So give me another sample problem or topic you want to go over, something that we haven't gone over yet, either in this class or somewhere else. Oh, where does this belong?
Oh, Miss Watkins.
All right, get it back to her. Did you tell her what it was for?
No, we actually just took it from the library, but we saw it in the hallway, so we asked her.
After you took it?
Yeah.
Always good. Do first and ask forgiveness second. Go ahead.
It still bothers me to this day. The floating, but like not
Sure.
submerged or something. The reason why I didn't get 100.
Buoyancy. Gotcha. We've got water. We've got water. What do you expect when you say that? We got water. We got the ocean floor. Okay. Now, two scenarios. Scenario one, the object is submerged. Scenario two, it is partially floating. Those are the only scenarios you have. If the object is floating at all, we don't really know the volume of the fluid displaced when that happens. If it's submerged, we do. If an object is ever submerged under a surface, the volume of the object is equal to the volume of the fluid displaced, because the object is what's displacing the fluid. So if the volume of the object were 7 cubic meters, the fluid displaced would be 7 cubic meters. Now, this case, when it's submerged, is 1. Other case, again, is this here, where the object is like this, and part of it is above the surface and part of it is below. No matter what, whether it's the top scenario or the bottom scenario, what's interesting or what's important is that the general equations of motion are the same. What force in both cases is pulling down? What force in both cases?
Gravity.
Gravity. So I'm going to draw a free body diagram over here. Okay, there's gravity. And what's pushing it back up? What's keeping this afloat? Buoyant force. And that's it. If there's anything else going on, it would have to be added to the problem. Like the example where we took a chain, God bless you, and tethered the buoy to the bottom of the ocean. So the chain was pulling down with tension. God bless you. So you'd have Ft pulling down in addition to Fg written there. So as a result here, what's interesting about these problems is that we don't have to really do too much practice with this. What we have to do is recognize that the free body diagram is the same. Now, two options. Either this object is at rest at the bottom, or it's at rest at the top. I told you already that if it were accelerating upward, it would be a similar problem. You would just have ma. If it's at rest in both cases, what's acceleration? 0. So in both cases, we could say the sum of the forces, and we're looking at the y direction here, sum of the forces equals ma. I don't need to do x and y like we did the other day with forces, because there's nothing going on horizontally. I mean, maybe there's like a motor or propeller pushing it forward, fine. But that's not affecting the vertical motion right now. Okay, this object we're saying is at the same vertical height. So as a result, we take a look at our sum of the forces. We say we've got FB pushing up, we've got FG pulling down, and if this object is at rest either at the top or the bottom, it's 0. If it's moving though, like if I'm holding it down at the bottom, remember you hold a beach ball underwater, what happens when you let go? Shoots out of the water. It has acceleration because the buoyant force exceeds the weight. Now, if the weight exceeds the buoyant force, it ends up at the bottom of the ocean down here, right? If the weight ends up being more than the buoyant force, it ends up at the bottom. But if it's at rest here and it's actually sitting on the floor, like physically on the floor, what other force would come into play? If we're sitting on the floor, sitting on a surface, what force comes into play? The normal force. So if we're looking at the bottom here, we might have to incorporate normal force. So we really have like kind of 3 scenarios, right? Scenario 1 is at the top. Scenario 2 would be in the middle. Scenario 3 is the one I just introduced, where like on the bottom, if it's actually at rest and the gravitational force exceeds the buoyant force, we would have the normal force acting up also. And we'd have to tack that onto this equation down here. So I'm just trying to show you how the scenario changes. The numbers, that's a whole other ballgame. We'll figure out the numbers, but that's the beginning point. But in all of these cases, we're not looking at any acceleration, so the overall ma would be 0. So let's take a look at this bottom case then, where we're at the bottom of the ocean floor. Let's say that the density of the object, or let's say, the mass of the object is 10 kilograms. Let's say that the density of the fluid is, let's say, what was water? Water's 1,000 kilograms per cubic meter. Is that what I wrote on your table? I'm trying to get a good number so it's more dense than water. Let's say it's 2,000 kilograms per cubic meter. The density of the fluid itself. And then the volume of the object. You okay? And then the volume of the object is 0.8 cubic meters. So that's our given information. We have the mass of the object, the volume of the object, and the density of the actual fluid. How are they going to come into play in this equation? Where are they going to play a role, those givens? Where are they going to play a role? What's the formula for FG? For FG, I'll start you up with a layup, a nice easy one. FG is always? Yeah. Shimon, what's FB? Oh, you did your hand up. What did you answer? Density of the fluid times the volume of the fluid times gravity. Okay? If you need to know, where is that? Yeah, it's on your reference sheet or formula sheet, either one you want to call it. So just look at the problem. You have everything. If we're trying to figure out the normal force pushing up from the ground, we could solve for Fn. We're given the density of the fluid. We're given the mass of the object. We're given gravity. Are we given the volume of the fluid, though?
No.
Not directly, right?
You can look it up.
That's density. When you look up density, you don't look up volume. It's completely submerged. Very good, Ariel. The volume of the fluid pushed aside equals the volume of the object because it is completely submerged. So in this case, VO was 0.8. You don't even actually use that anywhere. Notice that? You don't use VO because I gave you the mass of the object right here, MO. You don't have to replace mass with density times volume like we did in the past. So you might think, oh, this is extra information, but no. It turns out that VO is the same thing as VF because it's completely submerged. Okay, so a problem like this is a good example where you have to find the resulting normal force. But again, depending on the scenario, things will slightly change. Okay, depending upon the scenario. Let's go with a different question. I'll come back to you. Give me a sec. I'm glad you're prepared. Just give me a sec. Let me see if there's another question first. Another topic, so what do you want to work on?
Realize your schematic where it's like both parallel and...
Sure. Simplifying a schematic in parallel and series? Yeah. Oh, I'll make it up. Thank you. Let's say we've got power source here.
Oh, Mr. Hall, there was something happened during our math class today. Like the lights started flickering at the top, and then afterwards it started to smell like burning plastic. And then at first no one else smelled it, and I was like, it was so strong. And it got stronger and stronger. I'm like, should we probably turn the lights on because there's a shortage.
Something must have shorted out and it was burning.
But like this morning downstairs in the kitchen, like I came into school and like it was flickering downstairs too.
Interesting.
And then I went into math and then I was like, oh,
Paranormal activity. I wonder. What could have happened today that would cause that? I mean, there's temperature change.
Like there was no smoke, so there wasn't a fire, but like it smelled like when we can explain that and why the physics. What are those kind of
It happened because of the way it is.
Label these. Ready? Let's go. 5 ohms, 4 ohms, 3 ohms, 2 ohms, 7 ohms, and 8 ohms. And a 9-volt battery. All right. So the goal here is this. The goal for any problem where you have several resistors set up is to come up with an overall resistance so that you can find the overall current in the circuit. That's the reason you do this. Okay? So we have a 9-volt battery and everything else are resistors. Ohms everywhere. This is a 3. So in this problem, we have to look first to see where we can easily simplify things. The goal is to start easy. What would you start with?
Is that a 2 and a 2?
That's a 3 and a 2. Sorry, that's a 3 up here that I just tried to correct. So what would you?
Add them together.
Yeah, so start by replacing this piece here, and I'll show you what I mean when I circle it. Replace this with one resistor of what resistance? 5 ohms. Agreed so far? Again, 3 and 2 are in series. Replace it with one that is 5. I can't do much with 5 and 4 because it splits before it gets to the 4 here, right? See the split right there? So I have to take care of what's going on over here still. This is good. Now I got to do this piece, get one of these. Then maybe I could do something with these 3 that are then in parallel, right? But what do I do with these 2 over here? Yeah, so I've got 1 over RP equals 1 over 7 plus 1 over 8. Okay, remember, this is a reciprocal sum. Reciprocals for each of these parts. You could use your calculator to do this for sure. Don't do this by hand. I mean, common denominator is 56. That's a mess. You get 15 over 56, right? Which would then just be 56 over 15 when you invert both sides. So what do we end up getting when we do this? Either add them together in your calculator and then do the inverse, hit inverse, or you can use a common denominator if you actually so choose. Remember, RP is going to be whatever you get when you add these fractions together, but then the inverse of that. It's the inverse of that. Did everybody get a cookie, by the way?
I didn't know.
It's so funny the way some people are honest and some right away jump the gun.
How many cookies are left?
One for the Zodiac Killer and one for Ted Cruz.
But that's only, so that leaves one left. It's not the same person.
Let's take a look, please. They are the same person. What do we got? 3 point. That was really good. Wow. I didn't have any this morning. I had like 1 or 2 last night. They were good, but I didn't think they were that good.
They're better like in this.
Yeah, when they're kind of like moist like that, they're really good. Wow. All right. 3. It does taste like, kind of like a brownie almost, right? Yeah. So, listen. 3.8 ohms. Notice that that's smaller than both 7 and 8. Whenever you reduce something in parallel, it's always going to get smaller. So we put 3.8 as the resistance here and get rid of these 2. And we think of this as a single resistor now. So now we've got a single resistor here, here, and here. 3.8, 5, and 4. So I'm going to redraw this so we're all clear as to what's going on. This is 4. This is 5. What? You'll definitely have something with circuitry, for sure. Now, stop. Now, we've got resistor number 1 that was in the beginning. This 5 is a simplified version of 3 and 2. This 3.8 is the parallel part from 7 and 8. The 4 is given there. Here's the part that people make mistakes on, right here. The flow leaves the positive terminal. It continues through the first resistor. And then what happens right here?
So that means,
As soon as it splits, it means everything from that point on is parallel. So these 3 are in parallel. Not these 2 in parallel and then this parallel with that. All 3 of these are in parallel. Okay, so how are we going to go ahead and simplify that?
The same thing.
Yeah. And your answer will definitely be less than 3.8. It's always less than the smallest resistance. What do we get for RP? It should be quick math. Come on. Add them up, invert. What do you got, Ed? Now, if that's the case, that 1.4 replaces all three of these. So now I've just got 5 and 1.4. So 6.4. Okay? So now again, this circuit becomes this. Simply 5 that was here the whole time. That's the same 5 as that. And then the 3 that were in parallel are going to all be replaced with this single one that's 1.4. Which, yes, Sophia's right. These are now in series. So it would be 6.4 as an overall answer. Okay, that allows us to determine the current through the circuit. Isn't it crazy that it all works out that way?
I'm talking about that, and then the way you move things up.
Oh yeah,
Ah.
that's also like the app is in this.
The app is weird in this. It's real weird. You used it for your lab, 17.
Yeah. And
20-minute lab that you recorded.
It was
20 minutes. 20 minutes. How long were your labs for lab 17? 2 minutes? 3 minutes? 1 minute? Maybe 3 minutes? Carolyn, how long was yours again? 20 minutes? I sat there and she's like, so next, no, maybe I'll do this. No, I think I'll do this. She's zooming in, zooming out. I'm like, get to the point, Caroline.
I was just sitting there because I didn't want to do it.
I can tell. So you put me through the torture of listening to you think through the
Yeah.
whole lab.
Yes. I never want to do that ever again.
I thought you'd like that lab. I thought it was like an easy lab. No?
Paper and I will fill it out.
I thought you would like to explain things in your own words. Anyway. So, yeah, I mean, I guess. So you've got, listen, so you've got the voltage, you've got the overall resistance. You could take voltage divided by resistance to get the current. Okay, remember V equals IR. So to get current, divide voltage by resistance. 9 divided by 6.4 would give you the current supplied to this circuit. And the current is, again, the flow, right? It's the charge over a given time period. Okay? It's Q, really, the amount of charge passing in a given time period.
Let's just say we have to draw this. You said the thing is we have to draw it. If we don't I know the symbol for a light bulb and the symbol for a
No, it's going to mainly be this. A bulb just has a circle around it, but it's not a big deal, no. You should just know the idea of simplification of resistors in general. And back to Siobhan.
A hair dryer draws a current of 9.1 amps. How long would it take for 1.9 times 10 to the third coulombs of charge to pass through a hair dryer? How many electrons in this amount of charge?
And what was the first part? The current was what? How many amps?
9.1.
So this problem says that the current drawn, this is a good question for either multiple choice or a quick short answer. Okay, it wouldn't be heavy duty math unless it was like part A for a math problem. It says a current draws 9.1 amps of energy. The amount of coulombs that actually are used here are 1.9 times 10 to the third. And then it says how long does it take to do this?
How long does it take for the charge to pass through the hair dryer?
And then how many electrons does this represent? Those are the two things we're trying to figure out. Well, remember what current is. The definition of current is charge per unit time. Charge per unit time. Current, I, is defined as charge over time. And I think in class I might have wrote delta Q or delta T or something, but delta just means change, right? So how much time has elapsed? We don't know. We know how much charge is used, 1.9 times 10 to the third. We know the current is 9.1, so we can find time by switching these two. That's the easier part. The next part says, how many electrons is this? And a lot of you made mistakes on this on the test. I gave you examples where there were 20 electrons jump from one object to the other. So you have to consider how much charge that is. And a lot of people just wrote 20. It's not 20. What's the charge on an electron? Good. 1.6 times 10 to the negative 19. That's the charge, coulombs. So if you want to know how many electrons this charge represents, take the charge and divide it by the charge per electron. So type in your calculator 1.9 times 10 to the third divided by, again, 1.9 times 10 to the third. That number divided by 1.6 times 10 to the negative 19. I'll jot that down so you can see it. I'll explain. That's how I would see this, Shaban, so that might make more sense. 1.9 times 10 to the third coulombs, that's the amount of charge, over the charge per electron. What happens to coulomb? And this is in the denominator of the denominator, which bumps it up to the numerator. My units will be electrons, which is what you were looking for. How many electrons was the question? Okay? You'll get a huge number. It doesn't matter what. It's going to be really large, right? Because you're taking third over negative 18, so it's going to be something to the 22nd power. Yeah, it's going to be a huge number of electrons. Okay, but the concept here is that if I tell you 30 electrons are used, in that case, you take 30 times 1.6 times 10 to the negative 19 to give you the total charge. Okay, so let's go through what. Imagine something in space, some source that provides 32 charges of electron in it. It's negative, so the field lines are drawn inward. Okay, and the question wants us to figure out what is the electric field intensity 2 meters away from it. There is. What is the electric field intensity at that point X? 2 meters away. Give me the equation for this. I just want the equation for now. What do you got?
FE.
Not FE. That's electric force. See, that's where it gets confusing. FE is electric force. Yeah, KCQ over R squared. Now, it's very similar to FE, but FE is the electric force between two particles. This is the field around a source. Very different things. Two particles pull each other together or they push apart. It's one or the other. We did examples with 3 particles and you found FE using a free body diagram. This is an example of finding the electric field strength at a given distance. 2 meters is the distance. Kc is given. The issue here would be what is Q, but now that we've gone over this, we should be able to figure out Q right away. Well, Q is simply 32 electrons. So 32 electrons. That's Q. 32 times what an electron is. That's what Q would be in this problem. If it's 7 electrons, what?
Is it always negative?
Because it's an electron. Yeah, because it's an electron, it's considered negative. Okay. If it was a proton, it would be if there were a bunch of protons, it'd be positive.
We didn't mention Joe. Wait, we didn't think of that. Could you solve for Q with the equation?
Yeah, but you don't have E. You're solving for E, right? You're looking for E. Okay. If you're given E, then you can solve for Q, but that's a different question. You wouldn't be given this then if you were solving for Q. What else?
So you multiply and you give the number of electrons. You divide and you give it a charge.
Or you divide when you're trying to find the number of electrons. How about that? Okay. Different topic?
Yes.
What do you got?
Circular motion.
Circular motion. Okay.
I don't have a specific problem,
Yeah, go.
but the question is that there was one on test when we first did it, and for the fan, I think, and you were like, why are things drawn in, or like, why are things pushed out? Whoever it was, it was the reverse of the law. Like, it wasn't, usually things are pulled toward the center.
Okay.
Something was
Yeah.
so the fan was broken, and
Yeah.
that, something like that.
So, the easy example that Siobhan is thinking of is this concept. If an object is spinning in circular motion, the material on the outermost part of it wants to kind of fly away. Usually, there's something keeping the circular motion. Maybe it's structural integrity, the actual shape. Maybe it's some sort of a force pulling it toward the center. And that's usually provided by either gravity or a rope, friction, or something. Now, the example I gave on the test was a tire's wheels are spinning. And mud that's on the tire flies off the back of the tire. If you've ever seen a car stuck in mud and it tries to move, you'll see this tire spinning and the mud flies off tangent to the circle, literally tangent to the actual circle. In that case, when that happens, the reason it happens is because there is no FC in that problem. FC in that problem would be the friction between the mud and the rubber wheel. But there's nothing really holding the mud to the wheel, so the centrifugal effect makes it move away. similar if you think in medicine, a centrifuge. You put like a specimen of blood in the centrifuge, and it spins it fast enough so that parts of the blood separate based on its density, and you get different layers of what's in the blood at different radii from the center. Because objects, when spun in circles, want to move away. That's the centrifugal effect. Centripetal force, which is Fc there, that's the thing that actually keeps it in the circular motion. Okay, the centripetal force itself. A problem such as this on the final exam, you could consider. You consider a problem where I have you determine. We did one of these in class, if you remember, in the lab. You spun that rubber stopper. Remember the little pen, and there's a string. I could give you an example and say to you, the time it takes to complete a certain amount of revolutions is this. Determine the centripetal force acting on it. Well, if you have the time, you could find the velocity. You'll be given the radius. You'll be knowing the mass. You plug those values in to get the actual force. But it depends on the scenario. If something is moving in circular motion and you want to find the distance traveled, what do you use? What's the distance traveled around a circle called? Circumference. So if I want to find out what the actual velocity is, I could take the distance traveled, and this is really speed. This is really speed, just so you know. The distance traveled over time. If I want to find the distance traveled, I use 2 pi r over time. And what's interesting, actually, well, it's not going to work out perfectly, but r is in this, and r is over here also. So one of those would cancel if you actually plugged in. But if you're trying to find out what the velocity is, and maybe I gave you an experiment set of data. Expect to get that, guys. Expect to get data on the final. And you have to conclude stuff from the data, like you would do in a lab. So if I gave you 5 time trials, each of which had different times, but you knew the radius was the same every time, you might average those 5 time trials, use the average time, use the radius given, calculate the tangential speed, plug the tangential speed in here, use the radius given, and maybe you're solving for the mass if I give you the centripetal force, or maybe given the mass, you're finding out the centripetal force itself. Okay, another example of this could be like an object going through a loop-de-loop, like on a roller coaster, or a car around a track. I could say, find the frictional force that the tires provide to keep this in circular motion. Well, frictional force is centripetal force here. Because a car going around a track, it's friction that gives it centripetal. Remember, centripetal is not a real thing. The centripetal force is provided by something. A planet going around the sun is gravity. The proton going around the nucleus, electrostatic force. The car going around a track, friction. An object on a string, tension. Everything is provided by some other force, really. So, if an object is being spun, and I say find the tension in the rope, you're finding Fc. If an object is going around a planet, and I say find the gravitational force, you're really finding Fc. If a car goes around the track, that's when you're finding FF, really. You could use the other formula, but what if you weren't given that information? Say you were given an asteroid, and the specs on an asteroid's time of flight around it. Okay? Other questions? We still got a lot of time.
So light ray makes an angle of 20 degrees with a normal line with a boundary of linseed oil and water. Determine the angles beta 1 and beta 2. Note that n is 1.48 with linseed oil.
Okay, so this is a problem where you go through multiple surfaces. You did this on your problem set. The first material's n value was what? 1.48 for linseed, and the air is 1. Okay. So this was 1, and this was 1.48. So right away, the n value increases, so theta is going to decrease. And forget who said it yesterday. They were talking about theta. Sophia, you did. And I was like, maybe, remember Snell's law, ni sine theta I? So here we see n is increasing from 1 to 1.48, so theta is going to decrease. Shh, come on. So this next angle here, instead of continuing at 20 degrees, it's going to be something less than 20 degrees. Let's say we figure it out. How do we figure it out? Well, we use Snell's law. R, refracted. I is incident, R is refracted, initial and final. Now, let's say this angle, we do the math. You could do the math real quick and find out what theta R is actually. Just plug in this for theta I, NI, NR. You get the angle here. Once you have the angle here, you now have another situation with this, where you have a new normal. Here's your new normal, and now a new material. Let's say this new material is glass or water, whichever of the two, it doesn't matter. We now have an n value that drops from 1.48 to 1.33. So instead of bending toward the normal now, it's going to bend away from the normal. So if this angle happened to be, let's say hypothetically, the answer we get for this is 12 degrees, hypothetically. All it means is that this next angle is going to bend back away, and it's going to be something greater than 12 degrees. So this was a 3-step problem where you had this. But you'd have to use Snell's law to get the 12-degree angle, whatever it is. Then use Snell's law again with now 12 degrees as the incident angle, with 1.48 as the incident n value, 1.33 now as nr, and theta r, this angle down here, is what we'd be looking for. Another topic. Good question. Another topic. This was...
For this one, the critical angle is the angle that experiences total internal reflection.
Yeah, it's when theta r becomes greater than 90, remember? So look, if this angle here is 30, it's there. 45 is here. 60 is here. 90 would be right there, right? If this angle turns out to be greater than 90 and it ends up here, the ray means it's just doing this. That's what's happening. So if you ever solve a problem and theta r somehow turns out to be more than 90, it means you have total internal reflection. Okay? You could have total internal reflection, or I could say to you, determine the angle needed for total internal reflection, and then you'd have to use that other equation I gave you for theta c. Okay, it's on your formula sheet right below Snell's law. A different topic. Which one? Waves. You want to be more specific? There's a lot we did with waves.
The difference between, you said it's very hard, you're not going to be able to draw things with transverse waves. There's ones that go like this.
Yeah, longitudinal and transverse.
Yeah, and then you can't draw transverse.
Yeah, so here's what happens with transverse. With transverse, the vibrations are up and down. That was when I took the slinky, I forget who I did this with, and just kept going like this over and over. And you guys literally saw like a sine wave forming, right? Because the vibrations were up and down, but the wave was left to right. Transverse means perpendicular. So if the vibrations are this way, but it moves this way, that's perpendicular, transverse. Longitudinal is when we took the slinky and went like this and pushed, and a pulse went through the wave. The vibrations were this way, because the pulse would compress and decompress the spring, but the wave was also moving this way. That's when the wave and the vibrations are parallel to each other, as opposed to perpendicular. That's really the only two differences you should know with waves as far as the two types of mechanical waves. I mean, the amplitude of the wave indicates how much energy it has. We talked about that. Think about it, right? If I go like this, and then I go like this with that slinky, if I did the second time, the amplitude will be much greater because I'm putting a lot of energy into it. Amplitude is directly correlated to your energy.
Are you transferring heat?
No, you'd be giving it energy. I mean, some, I'm sure, but you'd be giving it energy in general, the metal you're touching, yeah. So you'd lose some energy there. What topic?
The speed of all electromagnetic waves in empty space is 3 times the speed of light. Calculate the wavelength of electromagnetic waves emitted frequencies, radio waves, and 80.
All right, I got it. So we're trying to figure out the frequency given the wavelength. There's one formula we have to know for this. What formula is it? We're trying to find the frequency or the wavelength given the other one. Given the other one, we're trying to find the frequency or the wavelength. What formula should we use for this? Yeah, so either I give you the wavelength and say find the frequency, or give you the frequency and I say find the wavelength. Either way. That's period, yeah. Period equals 1 over frequency. That's for that. But I'm talking about wavelength specifically now.
Would be wavelength equals 1 over,
No? Different formula, guys. Guys, again, this formula is if you have period and wavelength. If you have period and frequency. We're talking about frequency and wavelength. It's a different formula.
E equals
V equals?
frequency times the one that's like this.
Yeah, this one, right? Okay. the velocity of the wave equals the frequency times the wavelength. Write those words down if you don't know what these symbols mean. You need to know what these symbols mean, guys. Come on. The velocity, if it's an electromagnetic wave, is what? What's the number? You should know this number almost at this point.
9.
Yeah, 3 times 10 to the 8. It's the speed of all electromagnetic radiation in a vacuum. If it's an EM wave, you can automatically plug that in. Where is that number? It's on the bottom of your formula sheet. This is on the bottom of your formula sheet, C. C is the speed of light, or the speed of EM waves. So if you were given the frequency, you would solve for the wavelength, the number there. So let's say we're given the frequency is like 400 megahertz. All right, I want to figure out what the wavelength is. So I've got 3 times 10 to the 8th meters per second equals 400. Mega means 10 to the 6. So times 10 to the 6 hertz. And that's times wavelength. So you'd solve for wavelength here. What's up?
Light is an electromagnetic wave. Right?
Yes,
So
light is one of them, electromagnetic. Remember, the EM spectrum ranges. You've got infrared, you've got ultraviolet, you've got gamma, you've got radio, you've got light, meaning visible light. There's a lot of different parts to the EM spectrum. All of those would travel at that speed, though, all of them.
So when we're talking about the speed of light, we just mean the speed of all the
We mean the speed of EM radiation in a vacuum, yeah, which is the speed of light.
Just a broad question. Is there a particular like section that people tend to make mistakes on?
Off the top of my head, I don't know, to be honest. But what I would honestly recommend, as far as mathematical stuff is, there are a lot of mistakes with simple stuff like units. Know your units. A half a point here, a half a point there adds up. You notice that on your test. What else? Solving equations correctly. Be careful when you're doing that. When in doubt, plug in. When in doubt, plug in and solve that way if you don't want to solve algebraically. Multiple choice, be very careful that you look at italicized words. I say that all the time. If a word's in italics, it probably has an effect on the problem, right? Can't think of anything else. I don't know. I'm trying to find areas that you could do better in, but it's pretty reasonable. If you felt okay on the midterm, you should feel fine with the final. I mean, again, heavily second semester, but still first semester. I told you the format already. You know all that. Tomorrow after school, if you want to review, I'm going to be here for office hours tomorrow. I didn't do it today because I want to wait till we're kind of just done with the week. Okay? Yeah, definitely. Oh, this week you should have told me. I should have brought them in. We have a minute left. Maybe on Thursday if you want to see any specific ones, for sure. If you ever want to see them, just let me know. Come by and I'll show you your test. That's fine. You can definitely look at them. Okay, after school, either in this room or if there's already office hours from another teacher, we'll just go to another room.
Thank you.
Okay? Have a good day, guys. It's been a great year, obviously, guys. I'll see a lot of you next year. It's not goodbye yet. I know. Hopefully a lot of you are in my engineering class next year, though.
Keep these.
Study hard, please, if I don't see you. Yeah, I know, right? Study hard if I don't see you, please.